Hello everyone and welcome to the first lecture of the course Introduction to Algebraic Graph Theory. We see that in the introduction this course is about graphs and matrices. What was the starting point of graphs in our history? Apparently it was in 1736 when the great Euler solved the problem of 7 bridges of Königsberg, where he modeled the setup of bridges and land in terms of graphs. And since then, graphs are helping us in almost all the scientific analysis. Okay, matrices. The name matrices came around 100 years later, around in 1850, and two big names associated with the terms are J.J. Sylvester and Cayley. But the idea of matrix determinant came much earlier. It was around in maybe 1693, and the name associated with this matrix determinant is the great Leibniz. Okay, in this lecture we will have a quick warm-up on graph terminology. Maybe you already know this, but always good to have a quick recap. And towards the end of this lecture, I will give you a magic. Magic is based on the question from graph theory, but the answer lies in determinants. Okay, so a lot of exciting things are ahead of us. Starting phase will be just a warm-up, but towards end this magic will be, I will give you a magic question. Okay, very good. So how a graph look like? How a typical graph look like? A typical graph look like, so there are points and there are lines. Okay, so and these points are connected by lines. Okay, and by the way, now onwards I will never ever make use of these two words. Point will be replaced by the word vertex or node. Okay, and the term line will be replaced by edge. Okay, so for example here, how many vertex or nodes are there? There are 4 vertex. So let me number them: 1, 2, 3, 4. By the way, you can give some other name also: v1, v2, v3, v4. So no issue. And then lines are these. Sorry, I told you I will not make use of lines. So edges are actually, if you see, these are pair of vertices. So let me write. So vertex set is this, right? 1, 2, 3, 4, and the edges are this. So edge set I will denote with, suppose E. Edges I will, so E is nothing but a pair of vertices, right? So like a collection of pair of vertices. So like this 1, 2, then 2, 3. Then 3, 4, then I guess there are 2 more. So 1, 4, yes, and then 1, 2, 4. Yeah, very good. 2, 4. Now you might be asking why I am drawing it like 1, 2. Why not 2, 1? Okay, the reason is in this course we will be taking the graphs on which these edges are undirected. Basically 1, 2 is same as 2, 1, but there are variants of graph when you might allow direction. In fact, let me tell you about the variants of graphs. So variants, right? Variants. And in this course, fortunately or unfortunately, we will be not taking variants in general. Sometime we will be taking. So variants could be what? Directions on the edges. Directions on the edges. Okay, so for example, if you talk about, suppose this graph, there is no direction. This graph, if you talk about the real world scenario, this could be related with a Facebook network, right? Like Facebook. So suppose 1 is friend with 2, that means 2 is also friend with. But this is unlike Twitter network or some dating network, right? When some person or girl is liking boy 3, but 3 may not be giving any damn about 2. So in this case, this is a directed graph, right? So let me put some variant here. So let me draw the same graph here. So variants here. Yeah. Even though we will be not using much of variants in this course. So variants could be this. So there can be direction. Another variant could be this. There can be more than one edge between any 2 vertices. So suppose they like this, right? In case of undirected also, there can be more than one edge, right? So such edges we call multi-edge. Okay, multi-edge. Then third variant could be, there could be a loop. Basically an edge from a vertex to itself. Loop. third could be, fourth could be what? These edges could be weighted. Some weight is there. Suppose I get 12 weight, minus 12 weight, 3 and so on. So weighted. And these weights can be on vertices also. So weighted. But for this course, we will be not dealing with these variants. So our graph, our life is very, very simple, and we will call such graphs without all these variants simple graph. Okay, so in simple graph are what? So edges are undirected. Okay, there is no weight at all, and all these rest of the things are also not there. Okay, so very good. So now it is clear that why I'm not writing 1 2 and 2 1 both, because it is if 1 2 is there, it is obvious, then 2 1 is also there. Okay, now let us move to one very, very famous concept on graph that we call walks on graph, and in this course we will be heavily using this concept. Okay, so walks on graph. Okay, walks. What are walk? Okay, you assume that, let me take the same example. Okay, again. Okay, so for the timing, this graph will be friend of us, right? Because it will be helping us in and basically revising our matrix terminologies. Okay. You assume that there is some drunkard. Okay, maybe I can augment this friend of it. So maybe let me add few more words, and let me say this: 1 2 3 4 5 6. You can arbitrarily number these vertices. Okay, 1 2 3 4 5 6. Okay, very good. Now suppose there is a drunkard who is sitting at 2. Okay, so suppose this person is at, the drunkard person is at 2. Okay, now he is going from here to there, right? So a walk is basically a behavior of drunkard when he or she will go or traverse through these edges. So for example, one traversal could be this. Suppose this drunkard is, let me do it with a different pen, going to 3, then 4, and then it is returning to 3, and then it is going to 6. Okay, so if you see that this is a sequence of edges. So edges were what? So first it goes to, so this edge was there, 2 3, then it followed this 3 4, right? 3 4, and then again 4 3, right? I mean 3 4 and 4 3 are same thing, but I'm just writing the way it is coming back. So 4 3, or you can write it's 3 4 also, no issue, and then 3 6. Okay, 3 6. Very good. Now you see that in this case this edge is repeating. This is repeating, right? Repeating. Okay, a traversal, or basically when we are going from one vertex to different vertices and traversing through the edges, when the edges are repeating, such a traversal we call a walk. Okay, so and in mathematics term, or in more formal term, we can call this is a sequence of edges. This is a sequence of edges, right? And where the edges can be repeated. Okay, so let us write the more formal definition of this. Okay, so a walk is a sequence, I hope the spelling is correct, sequence of edges, and let me write these edges as E1, E2 up to EK, okay, EK edges, okay, such that, and for which, in fact, for which there is a vertex. So we have seen that the vertex sequence is also there, then 2 3 4 3 and then what was the 6. Okay, for which there is a sequence of vertices, let me number them, V1, V2 up to Vk plus 1. Remember, there will be just one more vertex, right? Okay, Vk plus 1, such that the end point, or you just see that Ek is Ei is basically nothing but Vi and Vi plus 1. Okay, for all i's, right? For right. So this I varies from 1 to k, right? So this is a walk, and I have already given this, right? So for example, what will be the corresponding vertex? What we call vertex sequence. The vertex sequence. This is S sequence. The vertex sequence is this. Vertex sequence here is very, very simple things to do. For this walk is 2, then 3, then 4, then again 3, and then 6, right? So I hope I am not make any mistake. Very good. Okay, now yes, you see that 3 is repeating, right? 3 is repeating. And by the way, length of walk is nothing but number of edges inside that walk. Number of edges the drunkard has taken to traverse this during the walk, right? So this is the length, right? So here, for example, the length will be k. So this is also called k is length of walk. Very good. Okay, so great. And now there are some special walks. These we call closed walk. Closed walk is a walk when the first vertex and the last vertex are same. A closed walk, very nice concept, and we will be utilizing this concept very heavily. Closed walk is when the first vertex is same as the last vertex. Okay, vk plus 1. Okay, closed walk. Very good. Now, so for example, if this guy has come from 6 and then back to suppose 2, then the starting and the ending point is 2, right? So this will become a closed walk. Okay, so very good. Now let us move to another concept that we call path. Okay, now path is kind of restricted walk. Okay, a path is a walk when vertices are not repeated. It is a walk where vertices are not repeating. Very good. The vertices are not repeating. So for example, is this red color traverser is a walk or a path? No, because the vertex here 3 is repeating, right? So a walk is what? So let me give you, a path is this. Example of a path could be this, right? Let me again make use of our friend. Okay, so this could be a walk. Path. I'm repeating the word walk. Okay, so this is a path, and let me number the vertices 1, 2, 3, 4, and this path is nothing but this, right? So first sequence of vertices is what? 4, 1, 2, 3. Nothing is repeated. So this is a path. Okay, very good. So it's a restricted version of path. Now since these vertices are not repeating, okay, edges are also not repeating. So edges are also not repeating. Very good. Very good. Okay, so I hope these concepts are, very simple, right? So nothing but just we are doing some recap of it. Now, next thing is about the connected graph. Okay, connected graphs. Okay. For example, again this. I told you that I will make use of this friend many times. Okay, so. Connected graph is a graph. If you see that in this graph, you can reach from any vertex to any other vertex traversing through the edges. Okay, so when there is a path between any two vertices, right, we call that graph as connected. Okay, connected graph. Maybe in simple term, every vertex, every pair of vertices every pair of vertices is having a path. Very good. Okay. So for example, in this graph, if you pick any two vertices, you can always have a path between them. Okay. What is not, the graph which are not connected, we call disconnected graph. Okay. So for example, this part, if you see that, is not connected. So this setup, if you see that, this graph is not connected. Why? Because you cannot reach, suppose if I number them 1, 2, 3, 4, 5, 6, 7, there is no path between from vertex 1 to any of 5, 6, 7, right? So this graph is not connected. Now next important concept is of subgraphs. Okay, the subgraphs are intuitively what? So there are vertex set in graph, there are edge set graph. What you do, you pick subsets of this, right? So you are picking suppose some subset of vertices, and you are picking edges which are incident on these vertices, those you have chosen as subset, right? But it's not always that you have to choose all the edges which are. So for example, if I talk about, so let me write this subgraph, right? Subgraph, okay, subgraph. So suppose I pick this subset, vertex subset S of this subset S. Suppose so vertex set are what? 1, 2, 4, 3, 5, 6, 7, and I am choosing S edge. Suppose this S equal to 2, 3, and 4. Okay. Now let me choose some edges of which are incident, whose the end vertices, or you may call the end points. I can use it, sorry. So end vertices are in this set. So suppose this, right? 4, 3, and 2, 3. So the graph will look like this. So the graph might look like this, right? So 4, 3, 2. So this is a subgraph. This is a subgraph, right? Now there is a very interesting and useful concept of subgraph that we call induced subgraph. In the induced subgraphs, you have to take all the edges whose endpoints are in the chosen subset. Okay, so induced subgraph. So subgraphs. So take all the edges. So this is a subgraph. Okay, subgraph, but not induced subgraph, because you haven't taken induced but not induced subgraph. Okay, very good. Now if you so because as 2, 4 is not there. Okay, so induced subgraphs take all the edges whose endpoints, or I mean here I can use endpoints. Sorry, endpoints are in S, are in. Very good, R in S. Great. So yeah, so the induced subgraph will be this. Induced subgraph will be this. Very good. Now this is induced subgraph. Now let us move to maybe the final concept that we will be requiring to later on giving you that magic. Okay, magical question. Okay, so yeah, so the concept of components, or rather connected components, component or simply component. Okay, many times I will be using this simply as component. Okay, component is this. So let me again draw this graph again. Okay, so suppose this was my graph. Okay, and I think there was, yeah, this part. Let me number it, number the vertices. 1, 2, 3, 4, 5, 6. Now before defining connected component, let me tell you there are 2 connected components. Now think about what could be the definition of connected component. Okay, why I'm saying this? If you see that there are 2 chunks of, subgraphs of a bigger graph. Okay, and no vertex in one chunk is able to reach other chunk, right? So but there, don't get carried about only this much definition, right? So let me formally write what definition is, and then I will tell you what is the beauty about it, right? What is the beauty about it? So connected. So it's a maximal connected subgraph. Very, very simple. There are 3 words. This part we have already know. I already seen. This part also already we have seen, right? Now, maximal means what? Maximal subgraph means you are adding vertices and edges to it, and you keep on adding till the property of the connectivity is maintained, right? The property of this connectivity is maintained. So, for example, I will first tell you a subgraph which is not maximally connected, that means it is not connected component. So let me tell you this subgraph. Okay, so 4, 3, 2. I am saying that this is not a component. Why component? Why this is not a component? Because you can still add vertex 1 to it and then edges to it by making it more, basically making it more larger, right? So it's in that sense this is not maximal, right? More larger, and still the connectivity is maintained, right? So I can still make it larger. Suppose now this part. So now, so 4, 3, 2. Again, now I can add 1 to it, right? by making it more large. Now I cannot increase it such that connectivity is maintained. As soon as I will add 5, 6 or 7 to it, the connectivity will be lost because there is no path from these vertices to any of 5, 6, 7. So this is a component. This is a component. Similarly, this guy is also component. So there are two components. So one component is this one. So one component is this, another component is 2. Very, very good. So I hope, so let us see what we have seen till now. So we have seen definition of graphs, very, very simple, the simple graphs, okay. Then the concept of walks on it, then closed walk, then path, okay. And then similarly we can call, so there is one concept that we call cycle, okay. So cycle is nothing but path where the first vertex and end vertex are same. So cycles are, let me write here cycles also. So cycles are closed paths. Very good. Okay, so first vertex and the last vertex is same. Very good. And then connected graph, okay, and then subgraphs of a graph, okay, and then what special subgraph that we call induced subgraph, then connected component, okay. Now we will move to very, very, very simple looking graph that we call tree, and I hope everybody has seen tree. I'm not talking about the tree in our real life, but yes, there is a very much similarity. The tree we will draw, and the trees we see in the real life. Okay, so tree is a graph which do not have a cycle, and it is a connected graph. So, okay, so trees are what? So tree is a graph which is connected, okay, connected and acyclic. There is no cycle and no cycle, C-Y-C-L-E, okay, there is no cycle or acyclic. Okay, so it has no cycle. Okay, so for example, this is a tree, okay, this is a tree. This is a tree. Okay. By the way, if I add 2 more vertices and edges, this is not a tree. Why? Even though it still do not have any cycle, this is not a tree. Why? Because it is not connected. Okay. So let me erase it. So this is a tree. Okay. Very good. So let me now number its vertices. 1, 2, 3, 4, 5, and 6. How many edges it has? The edges are, so let me number the edges, right? 1, E2, E3, E4, E5. There are 5 edges, 1 less than the number of vertices. Is this coincidence? This is not a coincidence. Whenever a tree has n vertices, there will be n minus 1 edges. So there are some DIYs with respect to trees that you have to, DIY is exercise which is known as do it yourself. Okay, so this term I taken from one of my friend Professor Nisad Kothari. So DIY is do it yourself exercise, and in this course we will see many DIY. Usually they are very, very simple. Okay, and some of the DIYs might be slightly advanced. Those we will see in the tutorial or your assignments. Okay, do it yourself exercise. So I will give you 3 DIYs. Okay, so first DIY is a tree on n nodes or n vertices has n minus 1 edges. Okay, another DIY is suppose there is a graph on n nodes and n minus 1 edges and n minus 1 edges. Okay, and if the graph is, and if the graph is not connected, the graph is, sorry, not a tree, then it is a disconnected graph. It is not connected. It is when it is not connected, or it has at least 2 components, then it is not connected. Very good. The third DIY is this. Okay, so very simple DIYs. Okay, maybe you already have the proof sketch in your mind by now. Okay, third is related to degrees of vertices. Now I have not told what degrees are. Degrees are nothing but the number of the edges which are incident on that vertex. So for example, degree of this, let me write this red color. Degrees here are 3 of this vertex is, maybe I think this slight problem with pen. Let me, sorry about this. Okay, so degree here is, for example, 3, here it is 1, here it is again 1, right, here it is 3, right. So number of edges which are incident, is there a vertex of degree 2? Oh, there is no one. Okay, very good. So now the vertex which has degree 1 we call pendant vertex. Okay, so let me first write the here pendant vertex, a vertex with degree, degree 1, okay. And so another one is similarly pendant where there is a pendant edge, an edge which is incident on pendant vertex. Okay, so pendant edge is an edge incident on a pendant vertex. Okay, so for example here this is pendant vertex, example of pendant vertex, and this is pendant edge. Okay, oh, edges by mistake, edge. Okay, good. So now third DIY is this. In a graph, okay, a tree on n vertices which is greater or equal to 2 will have at least 2 pendant vertices. Very good. Now it's time to give you a magic. Okay, maybe you are waiting for it. Okay, the magic is this. In every graph, in every connected graph, okay, you can find trees. Okay, so you can find, so let me again draw the same friend. Okay, so now inside this there may be many trees. So for example, if I write this, so this is a tree, right? This is a tree. It's a connected graph, right? And it has no cycle. If you just focus on this red one, this is a tree, right? So now there is some special kind of tree, those we call spanning tree. Spanning trees. Okay. So it is a tree which is covering all the vertices. A tree of a graph covering all the vertices, covering all the vertices. I will tell you what an example of it. Covering all the vertices, For example, this is a tree but not a spanning tree. This is a spanning tree. Similarly, there could be another one. So let me again draw this graph. This, right? This. What could be the another spanning tree? This could be another spanning tree, right? This is again connected graph and there is no cycle. So this is again, this both are spanning trees now. Now question is, a magical question is this. How many spanning trees are there in a graph? Okay, think about this question. Okay, now you might be saying that, oh, I mean there are n vertices, there are maybe m edges. Out of those m edges you choose n-1 edges and check that whether these n-1 edges are forming a tree or not, right? And whether they are incident on all the vertices or not. Okay, but how good is this approach? We will see that this approach is very inefficient. Okay, and a very good approach is in terms of determinants, okay. And this is actually a magic which now I am going to write. The answer to this question can be given in terms of determinant. Let me first write the matrix, and I will tell you, if you calculate determinant of the submatrix of this matrix, you will find it answer, okay. Keep on thinking why this will be true. So let me give you that magic, and then I will end this lecture. The magic is this. Magic, okay. What you do, you draw a matrix corresponding to this graph. So let me number this graph. So let me again draw this graph maybe. So here, okay. So 1, 2, 3, 4, okay. And let me first write a matrix, okay. The matrix is this. Let me, and you please keep on thinking how I'm drawing this matrix. So 2, then minus 1, then 0, then minus 1, then I will do the same thing here, minus 1, then I will do 3, minus 1, minus 1, minus 1, minus 1, then I will do 2, then what, minus 1, and 3. Now I will do what? I will choose any entry of this matrix. Suppose I chosen this one. I will delete this entry, this row and this column, right? Whatever is the resulting matrix, I will take its determinant, okay. I will take a determinant. The mod of this determinant will give you the number of spanning tree. If you calculate it, the answer will be here 8. The mod will be 8. This will give you the number of spanning trees, okay. Just keep on thinking why this. You may just check here that there are in fact 8 spanning trees, right? But why, how I draw this matrix, why choosing any entry and deleting that corresponding row and column and then taking out the determinant, the mod of this value will give you the number of spanning trees. Why? Keep on thinking, and we will reveal this the answer, or reveal this magic in the next lecture, and maybe next lecture also, okay. Till then, thank you very much and see you in the next lecture.